All right, let's work this problem. So the first step in this problem is to figure out what kind of problem it is. And as soon as we see that we're looking for the uncertainty in the speed, and it doesn't specifically say what the uncertainty in position is, but we use words that mean the same thing. So we know it to within that. So that's an uncertainty in position. So we could say the uncertainty in position is equal to 0.1 nanometers. So as soon as you see, oh, we're talking about uncertainty in position, uncertainty in electron velocity, we know this is a Heisenberg uncertainty principle problem. So right away, before we do anything else, we write down that there is a relationship between the uncertainty of position and momentum, and that product has to be greater than h over 4 pi. And then we look at it and say, wait a second, this is momentum. Okay, we're given uncertainty in position, but we're not given uncertainty in momentum. And at that point you have to say, is there another equation involved? And on the equation sheet you see that momentum is defined as mass times velocity. And if we were to look at uncertainty in here, we can see that uncertainty in momentum is going to be the uncertainty of the product mv, and for things where we know the mass perfectly, the uncertainty is just mass times the uncertainty in velocity. So at that point, we can do a substitution. So we're going to take this term, or this uncertainty in momentum, and replace it with the right-hand side, mass times the uncertainty in velocity. So we have delta x times delta p, but delta p is the mass times the uncertainty and the velocity, that all that is greater than h over 4 pi. Okay, now at this point we say, is there only one unknown? Well, we want to know uncertainty and the velocity. So the unknown, hopefully, is uncertainty and velocity, because we're looking for that, so let's circle that. Are there any knowns? Well, we were given the uncertainty in position right here, so we can circle that. Are we given the mass of an electron? Well, we could look on the equation sheet for that, because we're talking about an electron. And Planck's constant's always given an equation sheet, and of course we know what pi is. So there's really only one unknown. So we want to solve for that unknown. So we have to isolate it, we have to divide both sides by this. So we have delta v greater than or equal to, we have h over 4 pi, but since we're dividing both sides by delta x, we can put that over here, we're dividing both sides by mass. And I'll put m sub e because we're talking about the mass of an electron. So at this point, we've done the algebra. Before we go on, we want to check the units to make sure we did the algebra right. So we've got, let's see, Planck's constant is going to be joules times seconds. Pi is unitless, but x has units of meters. Mass of an electron has units of kilograms. And we wanted this to be meters per second, and this certainly doesn't look like meters per second. So what we have to do here is remember what a joule is. So let's go ahead and move this over here. We remember, the way to remember a joule, or one way to remember what a joule is to remember Einstein's equation, E is equal to mc squared, and to remember that this is energy, this is mass, and this is the speed of light. And once you have that, you can say, okay, I know energy has units of joules, mass has units of kilograms, and speed is meters per second. So if I square that, I must have a joule. It must be that these mean the same thing. And once you have that, we can plug in this definition of a joule into our original unit equation. So let's do that. So we've got, actually we could just do it in the same place we had the original problem. We're going to replace this joule with what we said a joule was, which is a kilogram meters squared per second squared. And at that point we look to see if there's things we can cancel, and we see that we can cancel a kilogram with a kilogram. We could cancel this meter with one of those meters. There's two factors of meter, we're just canceling one. and we could cancel seconds with one of these units of seconds. And if we look what's left, we have 1 unit of meter, 1 unit of seconds, so we've got meters per second. So we'll write down this is meters per second. And that's a good sign that we've done our algebra right. So we're happy this. We'll maybe draw a box around it to say we're happy with it. Let's go ahead and use it over here. So we just plug in the numbers. We do have to be a little bit careful because we want to put everything in base units. So Planck's constant is 6.626, 10 negative 34 joule seconds. We've got 4 pi. We've got the uncertainty in x, and we have to be careful. That's in nanometers. We wanted to cancel joules with meters, so we better put this in meters. So a nanometer is tiny, so 0.1 nanometers is even tinier, so we better have a small number. How big is a nanometer? Well, there's 10 to the 9th nanometers in a meter, or another way of saying is that a meter is, a nanometer is only 1/10 to the negative 9th meters. So we can write this as 0.1 times 10 negative 9 meters. So there's our uncertainty in x. And then we put in our mass of an electron, and we can just look that up in the equation sheet, 9.1 10 to the negative 31 kilograms. Okay, so notice what we have. All the units we're plugging in are the ones that when we plug them in over here, we saw that they canceled to give us the units we need. Okay, so at that point, we plug everything in, and this comes out to around 580,000 meters per second. And we should stop here and say, if we wanted to do the right number of sig figs, oh man, there's only 1 sig fig because our data is only 1 sig fig. So really, we'd be justified in rounding this to 600,000 meters per second. I accepted something more. You don't want to just plug in all the numbers in your calculator. I didn't take off on this quiz for that, but in the future, you don't want to don't write down something with 6 or 7 sig figs.